Hi, in this lecture we are going to study about LTI systems, but now in transform domain. And the concept which we'll discuss in this video is frequency response. So what are LTI systems? LTI systems are characterized by their impulse response. You have h of n, which is the impulse response of your LTI system, and if you take a DTFT, you get h e to the power j omega. So this is the impulse response basically, and if we want to write it as a block diagram, we will write it like this. X of n is a signal and you pass it through your LTI system and you get some y of n. Now let's study this h e to the power j omega basically in the transform domain. Now we will start with an example. Consider xn as a pure frequency omega naught. So it's a pure frequency e to the power j omega naught n. It's a complex sinusoid. Now what will be the response of the system to this complex sinusoid? It's very simple that we can compute the response by convolving it with the system's impulse response. So h of n is the impulse response of my system. If we convolve it with my x of n, I get y of n. Now let's put the values and see what are these. So my h of n, so basically this is a simple formula for convolution, h of m into x of n minus m, and you sum over all the m. Now what is this x of n minus m? This is e to the power j omega naught n minus m, but now I can, now e to the power j omega naught n is not a function of m, so I can take it out as common, and the remaining terms remain inside the summation. But what is this term inside the summation? It is the DTFT, right? So what we get essentially is the DTFT term, which is mind it, this is omega naught. This should be omega naught, and so I get h e to the power j omega naught, and then this e to the power j omega naught n is anyways there. So what we find out that a pure frequency e to the power j omega naught n is an eigenfunction of an LTI system, and the eigenvalue is h e to the power j omega naught. So basically it means if I pass this function into my LTI system, the output will be a scaled version of this function, right? And what is this scaling factor? This is called the eigenvalue, and this is my eigenvalue, and this is eigenfunction. So if I this is basically the meaning of eigenfunction and eigenvalues of an LTI system. So pure frequency is always an eigenfunction of an LTI system. Okay, now what does that mean? Okay, physically or in real world, how do I make sense of it? So, okay, what is the meaning of a pure frequency? Let's start with a sinusoid. Let me take xn as simply some a times cos omega naught n, where a is just some constant amplitude, omega naught is some frequency. Now I want to compute the response of the LTI system to this x of n. You can compute the DT, or you can compute the convolution, but simpler way is just, this is an LTI system, a linear system, so superposition, etc., all those properties will hold. So why not we decompose this signal into two complex sinusoids, and we know the response to this complex sinusoid, we know the response to this complex sinusoid, and from there we can construct my yn. But if I want to compute the convolution, that is also alright, but that will be taking some time. So we will just use this simplification to make my calculations easier. So what I get here, see the first term is e to the power j omega naught n. So this is an eigenfunction, so it appears as it is, and multiplied by the eigenvalue, which is h e to the power j omega naught. Right, now let's look at the next term. The next term is e to the power minus j omega naught n. So this is an eigenfunction, but the eigenvalue is h e to the power minus j omega naught n. So this is the output for this particular input. Now let's simplify it. So what is this e to the power minus j omega naught? We know that if we have a real h of n, basically if my LTI system is real, you can just put the values and you can derive this very simply, that then h of e to the power minus j omega naught is equal to complex conjugate of h e to the power j omega naught. Very simply, just expand it in terms of hn and you will prove this. And so what does this mean? This means that the magnitude of both e to the minus j omega naught and e to the power j omega naught, the magnitudes are same, and the phases or the angle, complex angle, that is negative. Simply, so this is the meaning of, so basically we have decomposed this into magnitude and phase. So okay, we got this. Let us plug these values back into this equation and see what happens. So we have this equation and we plug these values. So the magnitude term is common, and inside the brackets we have these two terms. We can see that this term is complex conjugate of this term, so basically it's a cosine. So what I get is a by 2, a and mod h e to the power j omega naught magnitude, and cos of omega naught n plus the angle. So what does this mean now? This means that in my system, if I pass a real sinusoid, the output is scaled by some value, and this value is called the magnitude response, which is basically an amplitude scaling. The amplitude is scaled by some value, and my cosine or the sinusoid is shifted by some phase. So this is my phase response or a phase shift. Basically it shifts the phase. So technically it is called as the magnitude response and the phase response. Okay, so this is what is frequency response basically. So frequency response means response of my system to a particular pure frequency, and we have now known that this frequency is an eigenfunction of my LTI system, and then I look at the response of this frequency. That overall response is called the frequency response, and it has got a magnitude and a phase, the magnitude response and the phase response. Right? So this is my basically the output, and now this part, this is a complex number which we can break down into magnitude and a phase term. So and this term is called the gain or magnitude response, whereas this angle term is known as the phase response, and we also represent it as theta omega naught, just for basically only the angle part we can call it as theta omega naught. Everything else is known, but just representation. So this is all about frequency response. So basically what we saw is any LTI system, if we want to study it in a transform domain, then we have some phase response and some magnitude response. These two things are essentially what defines an LTI system. And generally, if we are designing an LTI system, these are the two things which we are concerned with. How does my system will amplify my sinusoid, pure sinusoid, and how does it bring about a phase shift in my sinusoid? That's it. Thank you.